frequency is for the problem. And so to fully characterize the solution, you're going to need some way to describe A, B, C, and D. And so we can have initial conditions, which we know from before. The thing is, though, those only describe temporal ODEs, time dependent. That's all fun and good where we have like x of time equals 0 and x dot of time equals 0 for WT. But now we need some type of boundary conditions for whatever it is we're working with to describe the space-dependent terms. So let's go ahead and say that we have something that's fixed on both ends. If it's fixed on both ends, what does fixed mean? Like in the most literal sense possible.
Either side can move. If they're just fixed like a wall.
Can't move, right? Yeah. So what we're saying is, let's say this is 0, this is L, and x goes this way. Wx of 0 is equal to 0. It can't displace at all. And Wx of L is also equal to 0. So whatever it is, it can oscillate however it wants in the middle, but it has to stay here. This thing is a solid member, whether it's a string or a beam, it's going to have to like stay in one piece. So it has to remain continuous. It also has to remain differentiable. So like you can't have like random jagged things in it like that. Excuse me. So when we plug in these two conditions into Wx, I'm going to write that out now. We have 0 is equal to A cosine omega over C times 0 plus B sine omega over C times 0. Sine of 0 is 0. This evaluates to 1. Therefore, we have A equals 0. So now whatever it's going to be, we can eliminate this term because we know that A is equal to 0. So we just determined A is equal to 0. Now what's left is B sine omega C, or omega divided by C times x. We're going to evaluate L now. So we have 0 is equal to B sine omega divided by C times L is equal to 0.
Hey, Connor,
Yeah.
you erased the first first one you did. You erased it way too quick, like we couldn't see it.
Oh, I'm sorry. My fault.
No, you're good.
0 is equal to A cosine omega divided by C times 0 plus B sine omega divided by C times 0. So we're just plugging in this first boundary condition right here, saying that the displacement 0 at 0 is fixed. So when we look at this and we try to evaluate it, anything times 0 is equal to 0. So the inside of both of these is going to be equal to 0. Sine of 0 is 0. Therefore, this whole term is 0. Cosine of 0 is equal to 1. So this whole term evaluates to 1. All we're left with is A equals 0. And if A equals 0 with this boundary condition, that means that this whole term right here is not present in our solution. So this thing is only dependent on some type of sign. Now let's do the same thing again, evaluating this L boundary condition. 0 is equal to, we can skip this whole term because A equals 0 equals B times sine of omega divided by C times L equals 0. Alright? So because we evaluated this first term, or we evaluated the first boundary condition, we don't need the cosine term, which means that our solution is only going to be dependent on sine. And now we have to figure out what this interpretation means. So we can have any different number of multiples for frequency. Like frequency isn't constrained here in any way. And C isn't constrained here in any way. Well, I mean, we know that C is equal to, write this somewhere. We know this, but we don't know anything about frequency yet. But we know about L. So if sine is always equal to 0,
Shouldn't that be the square root?
yes, thank you. I knew I was missing something. Thank you, thank you, thank you. All right. So let's talk about sinusoidal functions for a second. If we have a sinusoidal function, right? If it's always equal to 0, where is this function? Yeah, that's sine. Where is this function equal to 0 within its period?
And pi.
Right. Jumping ahead of me there for a second. So we got 2 pi and pi. And if we kept going like this, just like she pointed out, it's any multiple of pi for this to always be true. So for this to always be true, and us evaluating this expression at fixed, we have m pi
Wait, isn't that 2n pi? Or no?
no, because
What?
it's also pi right here.
Okay.
So you see how like it's 0 here, 0 there, 0 there, 0 there. The odd terms of n with respect to pi
Okay.
are also solutions of it. So it's just n times pi.
Okay.
Oh, right. Zero product property. We know that this is some type of constant. So this can't be equal to 0. So now we can say that just this part is equal to 0. So sine of n pi is always equal to 0. Therefore, we can just drop the sine term and say that n pi is equal to frequency divided by speed times L. So now we boil this whole thing down to just this expression. We don't need to even worry about the time part because we know it's going to oscillate, just like this. And now we don't even need to worry about this type of function. We've constrained it down to frequency. So if we rearrange this expression for frequency, we have C times N times pi divided by L is equal to omega, where N is equal to 1, 2, 3, all the way up to infinity. Did any of y'all see that video that I posted on under the file section where I showed y'all how to do harmonics on the bass guitar? No? Okay. If y'all get a second this week, go ahead and watch that. I put together a demonstration talking about what this N actually looks like. It's a bit more intuitive because you can literally hear it going on instead of the more things you saw in class. Okay. So these are all half periods. Like you said, there's no 2 pi. It's
Yeah.
a whole period.
I was
trying to mock. I'm
I
not
was
trying to
thinking
mock
like
you.
pi
but-
over 2. I don't know
Yeah,
why I
yeah.
was being an idiot.
So we know the whole period is 2 pi. And if it were 2n pi, then it would look like different multiples of entire periods fitting in there. But as you astutely pointed out, it's just pi times n. So half periods also count. So if n is equal to 1, it's going to look like just a half period. It's going to look like just this. N equals 2, we throw in 2 half periods. And it oscillates like that. And then I'm sure you've seen how this goes on. If we hit three half periods, something like this, and then 4, and so on. It gets really nasty looking, but it's super cool. And that's for fixed. So We could go through exhaustively all the other different types of boundary conditions that we're going to need to know, but that would take a lot of time. So, for fixed, this is our equation. And since n can be equal to any integer, you can have any type of integer multiple of your harmonic, or excuse me, your fundamental frequency for the system. So when n is equal to 1, you have your fundamental frequency of the system being equal to c times pi divided by L, which is also equal to the square root of your tension divided by your mass per unit length times pi over L. You're probably not going to be given mass per unit length of your system, whether it be a string or a uniform beam. It's pretty safe to assume that you're only going to be using uniform beams for this exam, because if it's not a uniform beam, you have to figure out that A is a function of X rather than just being a constant. So let's talk about how to evaluate this mass per unit length. And this is why it's so important to stress that I use a lambda here instead of a rho. So, kilograms per meter. Kilograms per cubic meter. I want some type of proportionality constant between kilograms per meter and kilograms per cubic meter. Because most of the time, it's very easy to look up what the density of some type of material is. So, we can cross out kilograms on both sides. So we have 1 over meters is equal to something times 1 over cubic meters. You can just do square meters. Right? 2, 3, law of exponents, you subtract these two numbers, so you get -1, so this thing's going to go on the bottom. Therefore, what I've been doing with this dimensional analysis is we can declare that mass per unit length can be expressed as your cross-sectional area times your density. So now, all we need is a cross-sectional area of the member. If it's a uniform beam, we can find this. If it's a string, most of the time they have circular cross-sections, so we can just evaluate what the diameter of the string is, solve for area. We're given the density, we can find the mass per unit length. Plug it back in, we can find the frequency. So, let's talk about the intuition behind this formula that we just found for fixed. As I've mentioned several times already, I'm a bass player, so I'm going to use this with an analogy that I'm very familiar with, times pi over L. The frequency is the note we're trying to play, right? And if this note is flat, that means that the frequency I'm hearing is lower than what it should be. What I do when I pluck it and I hear it's flat is I want to raise up that frequency. So I want to increase this number somehow. The way I increase that is I turn a peg on the headstock of the bass that causes the tension of the bass to increase. And this makes sense. If we increase the tension of the string, that raises the value of this expression right here, and then raises that frequency. If I were to cut that string in half, and then reapply it somewhere and try and get that same tension, everything else the same, and I pluck it, you're going to hear twice the frequency because we have L as inversely proportional to frequency. And then thinner strings typically make higher frequencies So we understand that A is in the denominator, yada, 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 so on, so on, so on. Just making sure that y'all get like what's actually happening, what this function describes physically. Okay, so let's talk about different boundary conditions, and I'm not going to derive all of them again. You don't really need to derive all of them, you just need to understand what mode shapes are going to look like. Are we good with all this? Okay. So can somebody tell me what a mode shape was in another portion of the class, or another section of the class? Like from exam 1 and exam 2, what did we describe as a mode shape? The amplitude, okay.
The eigenvector describing the different mode, or the different modes, amplitudes.
So it was sort of like describing how different masses in the system respond to the same frequency. And in this case, since we have a function distributed over the length of something like a string or a beam, it's going to be the profile of displacement. So it's like the mode shape is essentially the whole w of x that we end up with. So omega is frequency, and w of x is going to be our mode shape. So, as we saw before, for fixed, it was going to be half period sinusoids. So we would see like 1/2 period, 1 period, 3/2 periods, 2 periods, 5/2 periods, so on and so forth. Because we had n pi as the solution to sine of omega divided by c times L equals 0. So, when we have something over x, we have something called nodes and antinodes. So like, let's say I had something like this. Can somebody tell me how many antinodes, nodes there are, and which one is which, and where they might be? All right.
The nodes are like across the x-axis, like the
It's
node
fixed in
displacement.
this case, sorry.
Node displacement is the nodes, so it crosses the x. And
So
the
how many?
antinodes are place of maximum
Right.
displacement.
Okay, so this is fixed. What we can do to determine what harmonic this is, what mode this is, by counting the number of half periods. So it's like, I see 3 bumps here. That's how I know this is the 3rd harmonic. And this is how I know that it's omega 3 or n equals 3. For this case, we have 3 antinodes. And what an antinode is it's the maximum displacement. And then similarly, or I guess conversely, naturally, a node is no displacement. What we can do to quickly characterize and identify different mode shapes and different boundary conditions is by counting the nodes and antinodes. And so as we pointed out, there are 3 points in here that show the maximum displacement, and there are 4 areas where the displacement is always equal to 0. And this is for fixed. So now what I'm going to do is I'm going to describe the different types of boundary conditions that we're going to see and the relationship between nodes and antinodes. So what we have to do is we have to set up the boundary conditions for our terms. Set up the mathematical representations of our constraints for our boundary conditions, and then we'll see how they are represented graphically, and then see how they relate to nodes and antinodes. Okay. So let's start with fixed. So for a fixed end, we know that Wx of 0, or excuse me, Wx is equal to 0. This makes sense. If we like grab a snake and we like put it down on the ground, it can move everywhere except for where you're holding it, because you're forcing it to stay still. You're keeping it fixed right there. Right? Okay. We also know that, let's say that, I'm going to draw this and hopefully it's not too morbid for people. Right? Holding the snake right here. And let's say that my fist is at 0, and let's say that its angle is also 0 degrees. So it's like representing the origin, okay? So if I'm holding it here, the snake is squirming. Right here, like if the snake's body is going to be aligned with how my fist is holding it, right? So at this point, the derivative of that function is going to also be equal to 0. So like, if we have something moving here, like that, not only is it fixed at this point, but the derivative is also equal to 0. Like, we're not allowing it to rotate at that point. And so that's where you get like reaction moments and stuff like that from statics. So we're also going to say that the partial of Wx with respect to x is also equal to 0. So these are our two constraints for our fixed end. And so for a pin end, we have something that is,
Why Wx, not just W?
because we're talking about mode shapes,
Okay.
which are spatial distributions rather than temporal. We already know these, like, it's well understood how these operate, like, temporally, like time dependence. It's just the same type of thing as the rest of this class before, where it's like you have, where it's 0, then it goes to a maximum, then it goes to 0, then it goes to a minimum, and then over and over and over in a sinusoidal fashion. So it's well understood. He's trying to get you to understand the spatial stuff because that's what's different than the rest of the part of the class. And with the spatial things, like, with the time dependence, the entire beam acts together all at once. So there's no spatial dependence.
Wait, does W have a unit?
It's,
This is meters, isn't it?
Well, Wx is meters,
Mhm.
Wt is seconds.
yeah,
Oh, okay.
it's in meters.
I got you.
Because it's showing you, like, by how much it's moving,
So it's the
like,
displacement.
away from equilibrium. Yes.
Okay.
Wx is displacement, and Wt is how it moves through time. Okay. So for pinned, if I have something pinned here, like let's say this is the hinge of a door. The hinge of this door is a pin. So if I open this door, the pin isn't going to move in space, like it's not going to translate, but it allows the door to open and close, which means that pinned end, we can have some angle here, but this still isn't going to move. So now the only thing we have here is that Wx is equal to 0. We have a reaction moment for a fixed end. So the second derivative should be null. Yeah, we can have that, yeah. So the second derivative at that point is non-zero. So we can have some sort of curvature. So like for a free end, we can have this. So tangentially, yes, it's horizontal, but there is some type of curvature here. So that's okay for a fixed end. For a free end, because there's no reaction moment that's allowed, you can have a first derivative not equal to 0, but because there's no moment or no reaction moment within the pinned end, the second derivative is equal to 0. So essentially what it's going to look like is this is 0, and it's going to have a derivative of 0, but it's going to like bend either way. It's going to have some type of curvature. A pinned end is going to be constrained, so it's going to this is equal to 0, and it can have some type of first derivative, but it's not curved at that point. So it's like you have a straight line locally
So
that represents it at that place.
should it be, it says not 0 right now for the second derivative, it's supposed to be equal to 0?
Yes, thank you.
Okay. And the second derivative is just curvature.
Yeah. So displacement, displacement is the function. First derivative is slope. Second derivative is curvature.
Okay.
This will all make sense in a second when we start drawing these out. Okay. And then for a free end, so for a free end, there's not really a constraint on it at all. So in contrast to fixed and pinned, we know that the displacement isn't necessarily constrained at some point. So the displacement at that point is non-zero. There's not really anything touching it. So, and there's no reason for it to like really bend at all. So this is okay if we have a first derivative. But we can't have any bending moment at a free end. So second derivative is equal to 0. So it's like we can have that. So it's like you can have a slope and you can have it displaced in some way, but it can't be curved at that point. Okay. What was the fourth thing in the homework? Because I remember these three just fine.
Fixed free.
Pin, fixed, free, free.
Okay. Yeah, then that's fine. All right. So, we have these. That's all fun and good. So you're going to be counting half periods for fixed. Okay. Somebody give me a boundary condition. Like fixed, free, fixed, whatever. Just
Fixed free.
fixed, free. Okay. We're going to assume that this is the fixed end. And this is the free end. Okay, and this is x, this is 0. So if we start to draw this, let's just assume that we're doing the fundamental right now. So we're gonna have one fixed end, which means that it has to be equal to 0 at this end, right? Because we're using this boundary condition. And we know that the slope is also equal to 0, so whatever we draw, it has to start from horizontal and then curve in some way. This will make a lot more sense in a second. Excuse me, oh my goodness. And then it has to have some non-zero curvature. So if we have the first harmonic fixed free, and the free end can displace, it's not going to have a, yeah, no, I got this right, okay. It's not going to have any curvature, so it's just going to like be straight, like a pool noodle. So like you shake the pool noodle, and then it's going to do like this, and it's not going to keep curving at the end, it's just going to kind of go off to its own local horizontal. So if we do fixed free, it'll look like this. You see how it has a curvature, and you see how it starts off as horizontal, but then it goes to non-horizontal and doesn't really keep curving. It kind of looks like it evens out to some type of slope. This is what our boundary conditions are telling us. So if I drew fixed free, start off horizontal, have some type of non-zero curvature, start at 0, doesn't have to really be constrained anywhere else. Okay, so let's do a higher harmonic to make this make a bit more sense. I'm going to do this. Drawing these ends right here. I'll just do that instead. All right. So let's talk about how we can tell what mode this is.